Okay, and we're up and running. All right, so the first machine it asks you to make is a melee machine. And the description is basically you're fed in this stream of ones and zeros. Each cycle you get an input, right? And it's just seen as that one input. You just sample it every pause edge clock. And what it's asking you to do is keep track of the number of ones. And if the number of ones that you've seen is divisible by 3, then output 1. If it's not divisible by 3, then output 0. Okay? So usually first thing we do when we're making any finite state machine is make S0, right? And then this is melee, so I don't put any outputs inside the state, right? And this is just going to be my initial state. And initially I've seen no zeros, no ones, right? So I can just say that maybe this state S0 is I've seen 0 ones, right? So that also means if I see a 0, I'm still going to stay here, right? But if I'm in state 0, I've seen 0 ones. Is 0 divisible by 3? Can I divide 0 by 3? What is 0 divided by 3? So can I divide 0 by 3? Yes. Right? There's no remainder, right? So let's call this state, if we wanted to give it a label, it's x, like my inputs, mod 3 is 0. Basically divisible by 3, right? So S1, I'll give you a hint of what I want it to be called. So x mod 3 equals 1. So now from S0, if I see a 1, if I'm in S0, it means I'm divisible by 3, right? So the modulus of 3 is 0. So I've either seen 0 ones, 3 ones, 6 ones, 9 ones, and so forth, right? So if I'm in any of those cases and I see a 1, that means the number of 3s the number of ones I've seen is no longer going to be divisible by 3, right? And now when I take the modulus of 3, what would the result be if I get one more 1? Modulus gives me what? The remainder, right? So if I'm at 0 or 3 or 6 or 9, all of those modulus 3 are 0, right? I see one more 1. Any of those cases. Now the modulus is 1, right? So if I'm in S0 and I see a 1, I go to S1, output 0, right? And then if I'm in S1, I see a 0. The number of 3s doesn't change, right? I stay. S2. What do you think this one is going to be? Right? So if I'm in S1, that means my current remainder is 1. If I see a 1, I add 1 to my total number of 3s. So now my remainder goes from 1 to 2, right? So I get a 1, output 0. And then if I'm in S2, My current remainder is 2. If I see a 0, the number of 3s does not change. So I again stay in S2, right? But if I see a 1, now my remainder would change from 2 to 0, right? Because once I get to 3, then that means I'm at the next threshold if this number is now divisible by 3. Right? So I would go all the way back over here. I get a 1, I output 1. So this is the finite state machine that you would need to implement, and it's asking for a Mealy implementation. So for a Mealy implementation, we're going to have 2 process blocks, right? We're going to have one process block to decide what the next state is, and that one is going to be conditional, like in the sensitivity list, have pause edge clock. And then the other process block will be purely combinational. The sensitivity list will be the state and the input, and it's only assigning to the output, right? And then there are many different ways to do it. I'm just describing one way. And then I have different examples that you can see on Canvas that go along with the lab. All right, so how much time do we have? We have 15 minutes. All right, so I don't think we have time to do this as pure discussion. So let's just again do this one together. So this is going to be a Moore machine, and then this is the description. My input is 2 bits. It's AN 1 down to 0. And then my output is just 1 bit. And the question is, when am I going to toggle the output? So let's just start with initially I'm in state S0. And I'm going to output 0. And then this is just my initial state. And then let's read this first statement. So if my input is 0, 1, and then 0, 0, that causes the output to become 0. If my input is 1, 1, and then 0, 0, that causes the output to become 1. So in state 0, we're still 0, but let's see if we can then keep track of when do we need to change to 1 for now. So let's make a new state, S1. This one is still going to output 0. But I just need to remember that I've seen this 1, 1 is all. So if I see 1, 1, I'm going to go to state S1. So my output is still 0. But now when I'm in state S1, I remember that I've seen the input 1, 1. So then if the next input is 0, 0, I'm going to toggle my output. Right? So that's how we get from 0 to outputting 1. I first, no, 0, 0. Yeah, so here, let me change to laser pointer. I'm in SDR. I see the input 1, 1, right? So now I'm still outputting 0, but now I'm prepared to toggle the output. And if I see 0, 0, I go to S2, and then my output gets toggled when I'm in S2. So first 1, 1, then 0, 0. And then let's just do the same thing for S for when we're 1, which is the first statement. So S3. This is still outputting 1, right? But in order for it to toggle, I need to see 0, 1, and then 0, 0, right? And then the other thing is this case 3. If I see 1, 0 in either case, I should go to my prep state, right? Because it doesn't matter what it is. If I see 1, 0 and then 0, 0, I need to toggle. Do you see that? Okay, now we just need to cover all of the other cases. So in S0, I have the case of 1, 1 and 1, 0 covered. But what about 0, 0 and 0, 1? In those cases, I just wouldn't do anything, right? Okay, I want to erase. All right, there, now it's gone. So one convention that is usually used, if it's not shown as a transition, it's assumed that you just stay. So just to keep this diagram not so messy, let's follow that convention, okay? So if it's not shown, you just stay. So for this S0, the cases of 0, 0 and 0, 1, it would transition back to itself. Okay. And then for S2, that's the case for 1, 1 and 0, 0. It would transition back to itself. But for S1 and S3, we have to add some transitions. Because if we get 1, 1, but we don't get 1, 0 afterwards, we have to go back to the other state. So if we have anything but 0, 0, so that is going to be, well, we also have to cover the case. If we get 1, 1 or 1, 0 again, we stay, right? Because that's still just toggle. But again, we're just not going to show that to keep it neat. But if we get 1, 1, 0, 0, what's the one I'm missing? 0, 1. If we get 0, 1, we go back. And then over here, it's the same thing, except the opposites. So this one is 1, 1 that we go back. And now we have covered all of the other cases. So if nothing is shown for a certain case in a certain state, it just means you stay. Is that clear? So this is the Moore machine that you will implement and test. So just while I pull up the next thing, the code for today is 132. So do answer that. But I did want to show you guys the example finite state machines I've added to the lab here. So I show 2 examples that you can use, but you don't have to use. So here, this would be one way that you can set up the finite state machine. So it's just all in one big process block. So the process, the sensitivity list is just clock. And then we have rising edge clock. And then the finite state machine that these examples are implementing is the Mars rover, like 0, 1, 0 detection? I don't remember. Or is it 001? 001 from the slides. And then we just have this case statement on the state. So when the state is at 0, and then we know that we can call it S0 because we put this thing. We have this new type. It's called state type. And the signal state is of state type. So that's how we can do the reference call rather than 00. So we can call it S0 in the code. And then within the state, the case, we have the if the input is 0, otherwise the input is 1, right? So we cover the case for this is what our output should be if our input is 0 and our current state is S0. This is what the state should be if the input is 0. This is what the output should be if the input is 1. This is what the state should be if the input is 1. And we just do that for all of our states. So you're just going to convert the diagram into this code. Right? So this is one way to do it. You just have one big process block. That's like we just talked about when we were talking about the divide by 3. You can also do 2 process blocks for a Mealy machine. One where you have just the calculating the next states, and you have the process is the sensitivity list is clock, and then you have rising edge clock, and again you have case on the states, and you have this if on the inputs, but you only output state. And then you have a separate process block for your outputs. And then this one would be purely combinational. It would be dependent on the states as well as the inputs as your sensitivity list. And then if you do it that way, then your output can depend on states and inputs. But now it can also change immediately with the input changing. Whereas this setup, it's all dependent on pause edge clock, right? So with this one, you can implement Mealy, but the output is not going to change until pause edge clock. But if you do the 2 separate process blocks and make sure the second one is combinational, then you can have the output change dynamically, not depending on clock. So that's that one. The other one I wanted to show you. This is a Moore machine. And this is a Moore machine implemented with 2 process blocks. So here is our first process block. And this would look very similar to the first process block of the Mealy machine if you implemented it with 2 different process blocks. The only thing is, rather than outputting directly to state with the Mealy machine, you need to be able to, well, actually you can just output to state. But you do need intermediate of next state, and then you would do in the process block state is next state for the Mealy machine. But here it is again, right? We just have the case statement, our different states, based on the inputs, which state do we go to for each state, right? State S2, input is 0, input is 1. S3, input is 0, input is 1, right? And then we have this default state. And then we have the second process block. And for a Moore machine, the outputs only depends on the current state, right? So that's why this process block for a Moore implementation, it's only sensitive to state. So your case is on state, and output is going to change based on state. Yeah,
And the melee version would be both state and input.
Mhm.
For that same question.
Yep. So melee version, you would have states, comma, inputs. And then within these case statements, you would have if statements saying if input is 0, else input is 1. Yes. It gives it any combination. But we are just saying that we want to work with symbolic representation. So yeah, so if depending on how many labels you put in here, it will create the correct bit width for you. And then it just assigns each label a unique binary pattern. So it's not necessarily that S0 will be 0, 0, or S1 will be 0, 1, or S2 will be 1, 0, and S3 will be 1, 1. All that really matters is that they are different, right? And if we have 4 states, we need 2 bits. So VHDL will figure that out for you. And then you can code with this symbolic representation, which is more readable, especially if you're going to give your states meaningful names, like how we called the divide by 3 states. I put the label S0, but I was also calling it X mod 3 is 0, right? So you can give them more meaningful names, and that can help you with reading the code. And then when you add them to the waveform, you'll also only see that inputs, well, not inputs, but this is an internal variable, right? Signal state is going to show on the waveform as S0, S1, S2, S3. So it wouldn't show up as the binary value unless you change it in the settings. So those are just 2 examples, right? So this one is the one process block. You can technically make it melee or more, but it would be synchronous melee if you did it as melee. And then the way that you could make it more is you just make sure that for either if input, that the next state is the same, because I mean the output is the same, because the output should only depend on the current states, not on the inputs. And then this one is strictly an example of more, because we have state only, not state comma inputs. So that is your lab. We went 1 minute over, but I will again stay here. We have office hours after. And do go over the lab material itself if you haven't before lab today.